In this section, we're going to take a look at some vector operations from a graphical perspective. So let's begin with vector addition. The sum of two vectors, so imagine you have two vectors and we want to add them. The sum of those two vectors, u and v, can be found graphically by connecting the terminal point of vector u. So we see in this diagram some random vector u, and we know that that vector, because of the arrowhead, that the terminal point of vector u looks like it's occurring at the point 1, 3. We're going to take that terminal point of vector u and we're going to connect it to the initial point of vector v. So vector v could be floating around in space, but we're going to pick it up and we're going to connect the initial point of vector v to the terminal point of vector u. All right, now we're going to finish out that triangle. We're going to connect them, and we say that the resulting vector is vector u plus vector v. Okay, so the sum of those two vectors just closes out that triangle. The arrowhead on that new vector, u plus v, that is purposeful. So u plus v, vector u plus vector v, is the vector whose initial point, its initial point, coincides with the initial point of the first vector. Its initial point coincides with the initial point of the first vector being that vector u, and whose terminal point coincides with the terminal point of the second vector, which was vector v. So that's why we see it that way. All right. So vector subtraction, the difference of two vectors. So we've got the same vector u, we have the same vector v, we're connecting them the same way. Those can be found graphically by changing the subtraction to addition of the opposite. So we're talking about, instead of writing u minus v, vector u minus v, we might think of it as simply addition of the opposite. Now, why that helps us is because we can then just use our vector addition properties. But what does negative vector v look like? Well, adding negative vector v simply reverses the direction of vector v. All right, so right now vector v looks like it is pointing toward, say, southeast. Watch what happens when we reverse that direction. Now it's going exactly the opposite of that. So now it's going northwest. And so we say that adding negative v, vector v, reverses the direction of vector v, and it adds it to the end of vector u. Okay, so just the opposite. The resulting vector, which is vector u minus vector v, or vector u plus the opposite of vector v, is the vector whose initial point coincides with the initial point of vector u, so right here, and whose terminal point coincides with the terminal point of vector v, or vector negative v. So we looked at addition and we looked at subtraction. Now let's look at multiplication. The process of multiplying a vector by a constant c is called scalar multiplication, where that constant is called a scalar. Scalar multiplication changes only the magnitude or the length of the vector. Scalar multiplication has no effect on the direction of the vector unless that scalar happens to be negative, in which case we've seen that the direction of the resulting vector is simply going the opposite, the direction of the original vector. Scalar multiplication multiplies each part of the vector. For example, the product of some scalar c and some position vector a comma b would be simply written as c times vector v, and it would be equivalent to the position vector c times a, comma c times b. Let's take a look at an example. This example says that we're given the position vector 2, negative 1, and we're being asked to find the following. For part A, we're being asked to find 2 times vector v. Another way of thinking about that is we're being asked to calculate double vector v. Okay, so 2 times vector v is equal to 2 times each piece of vector v. All right, so that means we're going to have 2 times 2, comma, 2 times negative 1, which is equal to the new vector, or the new position vector, of 4, comma, negative 2. All right, so what we're saying is that this new vector, 4, comma, negative 2, would be twice as long as the original vector. All right, and if you think about what that graph looks like, and we'll look at that here in just a second, that is the visual that you should be thinking about. Okay, so with that in mind, if taking 2 times v makes the vector twice as long, then taking half of the vector probably makes it half as long, doesn't it? So I'm going to take 1/2 of 2, the position vector 2, comma, negative 1. I'm going to multiply each piece. And that gets me the new vector of 1, comma, negative 1/2. So we'll take a look at what these look like here in the next slide. All right, so in the last slide, or the last piece of the video, we suggested that by taking the position vector 2, comma, negative 1 and multiplying it by the scalar 2, that it would double the length. All right, let's see if that's true. So this example says, given the position vector v, which is 2, comma, negative 1, let's just go ahead and plot that. Sketch the graph of the following. Okay, so position vector v starts at the origin, 0, 0, and then goes 2 to the right, and it goes down 1. Okay, so here is vector v. There is vector v. Okay. The new vector, after I multiply it by 2, is the position vector 4, negative 2. So again, starting at the origin, but now I'm going to go to the right 4, and I'm going to go down 2. And does it appear that that is twice as long? I would say yes. We would only know for sure, however, if we actually calculated out that magnitude, which we could do, right? We could do that. What is the magnitude of position vector v? Well, position vector v, let's see, the magnitude of that vector, let me just go ahead and write this here, would be the square root of 2 squared plus negative 1 squared, which would be what, 4 plus 1, so the square root of 5. All right. What is the magnitude of, let me do a different color here, what is the magnitude of vector 2v? Well, that would simply be the square root of 4 squared plus negative 2 squared, which would be 16 plus 4, which would be the square root of 20. Now, is the square root of 20 twice as long as the square root of 5? Let's see here. Square root of 20 is the square root of 4 times 5, and the square root of 4 times the square root of 5 is equal to 2 times the square root of 5, isn't it? So, sure enough, It is twice as long, isn't it? Okay, using that same idea, I bet I can convince you pretty easily without doing it, but you should try it on your own, that taking half of the vector would make the length of that vector half as long. So that's going to put me at the new position vector, starting at the origin, going to the right one, and then going down half. So it's just half as long, isn't it? Okay, let's look at some more examples. In this example, we're being asked to describe a scalar multiple of a vector. So use the vectors, we've got all these vectors on the page here, use the vectors below to sketch the following. Okay, we're just sketching. So vector D plus vector F. Okay, so vector D is, looks like it's starting at negative 1, 1, and that's its initial point, and then it is going to its terminal point of 4, 2. And vector F, I'm going to pick vector F up, and I'm going to connect this initial point, I'm going to connect that to the terminal side of vector D, okay? Now, here's where it gets a little bit tricky, okay? Because I can't actually pick that up. But what I can do is say, okay, so with the initial point of vector F, I would have to go to the right 2 units, and I would have to go up 3 units, right? That's actually the position vector, isn't it? So I'm going to do that same thing, and maybe let me just put this in red. So I'd have to go 2 to the right, and I'd have to go 3 up. So I'm going to do that same thing. I'm going to go to the right 2, and I'm going to go up 1, 2, and 3. Okay, so that's how I make sure, this is vector F, that's how I make sure that I am actually getting the same length and the same direction. Okay, now the new direction that's formed, the new vector that's formed, what we've just created, if we close off that triangle, this is the vector D plus vector F. Now, one thing you might hopefully be thinking about is, how come there's no arrows over the D and the F? All right, so notation. There's 2 ways to express a vector. If you have the ability to write in bold font, then writing in bold indicates that something's a vector. Okay, so the type on this page is bold, right? We can definitely see there's a difference between what I've written in the problem, that D with the arrow above it, versus the D that was already on the page. That was bold font. For us, handwriting, unless we're really going to press hard, we can't do bold print. And so that's why I say always to put the arrows, the vector arrows, above the vectors themselves. Okay? So we have taken care of sketching vector D plus vector F. Now let's go to part B. Part B wants us to take 2 vector C's and then subtract vector E. Okay? So let's see here. I've got vector C down in the 3rd quadrant. It looks like it is having an initial point at -5, -2. There it is. And then it has a terminal point at -2, 1. Okay, so it's terminating right there. I want twice that vector. Okay, so I'm going to take and lengthen this by 2. Okay, so instead of going up 1 and to the right 1, 2, and 3, I'm going to do that one more time. Up 1 and over 1, 2, and 3. That is like me taking, it's really like me taking vector C plus vector C, right? Which is the same thing as taking double. Okay, so this whole thing is 2 vector C's. Now, what I want to do is I want to start on this terminal point of vector 2C, and I want to subtract vector E. Okay, now the way that I subtract vector E is by adding the opposite of E. Add the opposite. Okay, so what I like to do is first put in, what if I was just adding vector E? Well, if I was going to add vector E, and let me just erase some stuff here because it's getting a little bit messy. Let me erase all of this. Hopefully you wrote all this down so you've got it in your notes. Oop, a lot of things to erase. Okay, so if I was going to pick up vector E, right, here's vector E. Vector E has an initial point, and then it goes to the right 1, and it goes up 2. So I would go to the right from this terminal point. I would go to the right 1, and I would go up 2. That would be me adding positive vector E. I want to add the opposite of vector E. So instead of going to the right 1 and up 2, I'm going to do the opposite. I'm going to go to the left 1, and I'm going to go down 2. And that's what gets me the opposite. Okay, so if I was going to the right 1 and up 2, that's vector E. If I go to the left 1, so I went to the right and then I went up, now I'm going to go to the left and I'm going to go down. That is actually the opposite of vector E. And adding that opposite is what gets me the subtraction. Okay, that's what gets me the subtraction. And so this new vector, let's see, so I have 2 times vector C, and then I'm going to add that to the opposite of vector E, and the new vector is down on the bottom, and it connects the initial points and the terminal points. So that is the new vector.